Okay, now that our 1 second clock signal is generated properly, we're gonna check um, the output of the actual digital clock, the 24-hour clock. We're gonna pull here first the clock and reset the global reset. We're gonna also going to get the 1 second clock signal just to monitor that, and maybe the reference for the 1 second clock signal, that is gonna be 8. Let me just save it. Mm, Let's recompile everything. We restart the simulation and we run it a little bit. Okay, so we have here our 1 second clock signal that is taking about about 8 clock cycles to generate. I mean 16 clock cycles to generate a one clock cycle of the 1 second clock, assuming this is gonna take 25 millions, I mean 50 millions in the whole clock cycle. Okay, so we're gonna check. The way to debug this is we have this as our diagram for the digital clock. We have two counters for the seconds, two counters for the minutes, two counters for the hours. We're gonna focus first on getting the seconds. This counter should be incrementing its count every time we have a one period of a 1 second generated here. And we should see it go up to 9, and when it reaches 10, the comparator will generate a 1 that is saying that this one has finished. Remember that in a clock, this one goes up to 10, I mean up to 9, and then when it gets to 10, this one goes to 1, and this one goes up to 6, and when it goes, I mean, it goes to 5, and when it goes to 6, this one increments, and both of these are resetted every time they reach their count. Okay, so we're gonna check the first one, that is the 1 second clock. We're gonna check it. And for that, we're gonna go to our simulation and we're gonna click here on the device under test digital clock. And that one has the output of the count 0. Let's change the radix to unsigned. And then we see here that it's an X. That means that the counter doesn't know which value it has. So there's a problem here to start with. Okay, another thing, we don't focus yet in the binary to 7 segments. That's gonna be our interface to the output, to the actual 7 segment displays, but we don't focus yet there because it's easier to debug the output of the counter. Okay, so this one, we have an X at this point. So if we have an X, the comparator doesn't know when to output the that one here. So we want to check, we want to debug why this one is not outputting the correct value. So we go back here, we go to our counter 0, and then we're gonna check all the internal connections and inputs and outputs for that counter. Okay, so we reset the simulation. Oh, we already have them simulated. And if you see, we have the enable being one here, but still the count doesn't move to anything. Um, why is that? And the thing we can see here is if we zoom in here, we can see that the reset is always 0. I mean, it's properly connected because it's green, so it's not unconnected, but it's always 0. Why is that? So we want to go back and see this output here is always 0. So that means that your counter never starts at 0 because it's never resetted. Okay, so that we go back to the code and we see that the first counter is the reset of the first counter is connected to the output of the FSM. We can see this, that is here in the FSM, is here. So that is connected to the first bit of the FSM. So we pull that from the FSM. We click on the FSM. We have the reset signal. We select the first bit, the one that we're using, and we can see that they match. So they are properly connected, but the FSM is always 0. So we go back to our our state machine diagram, and we can see that from the table, the reset of the first counter is in S1 only until state 4. That means in this state, the reset of the counter 0 is 1. That's when your counter will reach the the count and is gonna be resetted. But there's a problem here because to get to state 4 from state 3, we need to check the output of the comparator 0 to be 1. So we need a 1 here to generate this reset to make this 0. Though those two things don't happen until state 3 and 4. So, but the problem here is that this one is going to be resetted until we have a 1 here, but the 1 here is not going to be achieved until this one reaches 10. How do we fix that? Okay, we are missing something here on this diagram that we want to reset this counter or all the counters when we have a global reset um, of the system. So how do we fix that is we go here and we're going to make an OR gate, and the output of that OR gate we're gonna connect it here, and we're gonna OR, and one of the inputs of the OR gate is gonna have the global reset of the system. So whenever we reset the whole system, all the counters go and are initialized at 0, and we're gonna give the reset of the state machine so we can control them over the operation of the clock. So we're gonna create that in here. I already have it. We're gonna create this signal reset 0. I already created here. And I created one for all the counters because we found a problem that is gonna be common for all the counters in the digital clock. So I created already here. We're gonna create an OR gate, and that OR gate is gonna be in one of the inputs. It's gonna have the output of the state machine for the reset, and the other input is gonna have the reset, the global reset of the system. Okay, so we're gonna make that change, and then in here we're gonna connect only the reset 0. Okay, so we save that. We go back to the simulation. We can see that if we did a change and we have a question mark here, so we have to recompile that because it was changed out of the ModelSim software. We have to recompile. Now that there's no errors, we can restart the simulation and we can run it. Okay, now we can see that it is not unknown the output. Okay, so let's zoom out. Okay, we're gonna change this to mm, radix to unsigned. And then we can see that is, since everything is connected properly in the counter, we're just gonna check the count again. And now we can see it. We run another. We can see that the count here, the initial count, is changing from 0 to 1 to 2, and it continues, right? So this is in the rising edge, and it takes a couple of cycles to update the a one clock cycle to update the count. Okay, so that means that now our counter is functioning properly. Now, the next thing to check is, let's delete all this. We select all, you selected clicking the first one, shift and clicking the last one, and then we can delete that. Okay, so we can continue simulating to see if we actually get to the ninth digit, and then the next second we reset. So and then this happens here. Let's check. Okay, now we can see it. So if we zoom out a little bit, we can see the count of the first counter that is right here is going 0, 1, 2, 3, 4, 5, 6 until 9. And the next second count, it goes back to 0. So that's what we want to see there. One thing, sometimes if it goes more, there's something that we don't have in this diagram is the reference for that comparator. That reference is, we have the comparator here, the first comparator. That reference is gonna be 10. So when we count 10 seconds on that specific counter, we're gonna reset that count and we're gonna increment the next one. So now we know that this one is working properly. We're gonna check now the other one that is we're gonna add, and we can add all of them now that we know that the first one is uh, correct. We're gonna the number one, number two, and number five. We're gonna reset, and now we're gonna run a lot more time. Maybe like 100 microseconds. Then, okay, we're gonna change all of them to the radix to unsigned. Okay, zoom out. Okay, we can see that if we zoom on here, okay, so we're gonna check the count 0. It goes up to it goes up to 9, and then it goes to 0, right? From 0 to 9, 0 to 9. The second counter for the seconds, it goes up to 5 and it goes to 0. And that's what we expect to happen. So when these two reach their maximum, the seconds counters, we want to increment the minutes. This one is the minutes right now, and we can see that it's incrementing to 1 after 59 seconds. So it's until now it's working properly. So we have 59 seconds here and a minute. So let's continue simulating. Let's now simulate 1000 micros. And let's zoom full. Then we can see 1, 2, 3. Okay, so this one is the seconds. You can see that it's just too condensed that is not possible to see. We know that this one is changing up to 9 as well. And this one, that is the second counter for the minutes, it is going to 5. And we want to check here if it goes, yeah, it goes from 0 to 9 and then 59 seconds. That increments the hours. So we just need to check that our hours are correct. So we have 1 to 3 to 7 hours. We need a little bit more and a little bit more and a little bit more. Okay, we're getting close to finish. Okay, so now we can see that it's working properly. This is the hours. This is the tens of hours. So it goes to 10 hours, 20 hours, and when it after 23 hours, when we reach an hour here in the previous in the minutes counter, um, we reset after that. Okay, so our clock is working properly. How to debug that is as we did with the counter. If something is not giving the value we're expecting, we check all the connections around that component. If all the connections around that component make sense and are correct, then the problem is going to be inside the component. If maybe we find the error that is outside, like in the case of the reset, that it wasn't the component itself the problem, it was the connection we had here that we were not resetting with the global reset. You can, if you have still problems, something that a lot of times causes problems is the state machine. You want to have the next state, the current state and the next state both in um, uh, unsigned. So we can follow it and we can just restart the simulation. Oh, you run it? Okay. So we're just gonna run that because it's gonna be a lot. We're gonna check the very beginning of it to see if you see it's going from 0 to 1 to 2 to 3 and then 0 to 1 to 2 to 3. So it's in that part is repeating this cycle. So it counts a second, goes to 3 and checks for the first counter to finish and then goes back. And then after the first count goes to uh, 9 on the 10th, we should see that it goes to the fourth um, state. So there's 5 seconds, 6 seconds, 7 seconds, 8 seconds, 9 seconds. At this point, it reaches 10 seconds, so it goes to 4 and 5. So it does this jump. When the first comparator, it goes to 1, it goes to the state 4 and state 5. So you want to check that the output your current state is following this pattern as you expect. And uh, if something is not, if it's not following this, you can add the next thing to check is you check this table against the outputs of the FSM. So you can check it like this. Let's just select the reset or the enable of the counters, and we're just gonna check the first two. Okay, so okay, let's move this one. This is counter 0, counter 1, the enable. So we're gonna restart. Then we're gonna simulate for half the time we were doing it. Simulate. Okay. So let's zoom in. If you see, we count. This is the way to check. The the enable of the first counter is gonna be 1 on state 2, and the enable of the counter 1 is gonna be 1 on state 4. So we go here and state, let's get rid of the next state to keep in the state 2, we have the first enable for counter 0 as 1, and you see your current state is 2 and then your enable is 1. Your current state is 2, the enable is 1. So now we check the second. We said that one should be on the fourth state, right? So we see it from here on the fourth state. Our enable one should be 1. So you check here. Our current state is 4 and our enable one is 1. Okay, so that's how you check that the FSM is generating these outputs properly. Okay, and this is how you debug the the digital clock. You have to check, you have to know how every counter and every part of the circuit is expected to work, so you can actually be able to debug and check if the signals are correct. But it is important that you have this diagram and this other diagram and this table. It is important that you have them in hand to be able to properly debug your code.